What we want to introduce now is the concept of Cascade Refrigeration systems. And in this case, it enables us to get to very low temperatures if we wish. And it's like having two stages of compression, but it's done a little bit differently. And so let me draw a sketch of this and we can see the advantages of it. And so we'll have the upper level, condenser, I know watching me draw things is not the most exciting thing in the world. And so we're going, and then I'll have another stage of compression coming off here. So if we look at this, so what's happening here is this is our low temperature heat in. So we'll have here, here's the Q into the system. Then Q dot into the system. Here's our compressor work coming in, so I have my power there. I'm going to discharge in this, rather than being a condenser, it's I have a liquid in here. It's the same refrigerant, so this is a direct contact heat exchanger. And so I'm going to be running this at a lower temperature. It's going to cascade around and we'll see what happens here. So let me number these. So we have 1, 2, 3, 4. And now this we'll have is 6, 7, 8, and 5. And let's look at what this looks like on a TS diagram. And so this would be 1, 2, 3, 6, 4, this is 5, and we have 6 to 7, 7 to 8. So if I look at this, so anyway, now I've drawn this diagram. So when I look at this, compared to one stage, so if I had one stage of compression, it would go from 8 all the way down to here. And so if I had one stage, it would keep following this line. So by having this cascade system, we have this is our increased refrigeration effect. So that gives us the increased refrigeration effect compared to one stage, and importantly we have this is the decrease in work. So we have two things. We're able to increase the refrigeration effect and decrease the work required. And now I'll go through an example with this for a 30-ton two-stage system using this cascade design, and we'll go through and we're going to find the optimum interstage pressure the same way that we had done before and look at all these. And so let's see, so we have a 30-ton R12 two-stage cascade. And it's minus 20 degrees Fahrenheit is the low temperature. sat temp for condenser is 120 degrees Fahrenheit, and we want to find the flow rates in the various fluid states. So here, we're going to have a flow rate here and a flow rate here. And I believe I call this M.1. And so we have that going on. And so we have all this information going on. I'm going to have to erase some of the board simply because there's not enough space to write. And so we're going to have the optimum interstage pressure. So we're going to have, we need to know what this pressure is to minimize the work. And we found that out for two stages of compression. So Psat at 120 degrees Fahrenheit is equal to 172.3 psia. And so then the optimum is the square root of 15.2, which is Psat here, times 172.3. And so we have that P optimum is equal to 51 psia. So we don't have tables for 51 psia, so we'll use the 50 psia tables. And we don't have superheat tables for 172.3 psia, so we're going to use 50 psia and 175 psia. So we'll use those for the table values. So now I have to erase something. I'll erase this. So H2 is equal to H sub G at minus 20 degrees Fahrenheit, which is equal to 75.11. S2 is 0.1710. P3 is equal to 50 psia. And S3 is equal to S2, and therefore H3, you look up in the superheat tables, is 83.81. So this is just going through the tables as we've done before. And we're using R12, so we have that. And then for H6 is equal to H sub G at 50 psia. Is 81.2. S6 is equal to 0.166. P7 is equal to 175 psia. S7 is equal to S6. And we get that H7 is equal to 91.1 BTUs per pound mass. I still have more stuff to find, so we still have to go through here and find all the other states. And it's important that you draw this TS diagram, because otherwise finding a state you lose track of your numbering system and everything else. So H8 is equal to H sub F at 120 degrees Fahrenheit. So that's equal to 36. And this is equal to H5. So we have that. And H4 is equal to H sub F at 50 psia, which is equal to 17.2. And H1 is equal to H4. And so at this point, we have everything. So it's taken a while, but we have all our enthalpies. So I can find Qn is equal to H2 minus H1 is 75.11 minus 17.2. So Qn is equal to 57.9 BTUs per pound mass. W23 is equal to H3 minus H2 is equal to 83.8 minus 75.1. So W23 is equal to 8.7. And now I'm going to find W67. So this is equal to H7 minus H6. 91.1 minus 81.2. So that's equal to 9.9 BTUs per pound mass. So what we're doing is we're doing everything per unit mass, and with that, it makes the numbers easier to conceptualize. So now let's find the total work. W total is equal to 8.7 plus 9.9 is equal to 18.6. And the COP is Qn over W total, 57.9 divided by 18.6 is equal to 3.11. So we're able to find the coefficient of performance for this. And we can find the mass flow rates for the various cycles. So Q dot N is equal to m dot times Qn. So we have 30 tons times 200 BTUs per minute per ton is equal to m dot times little Qn, 57.9 BTUs per pound mass. So we find out that the mass flow rate is 103.6 pounds mass per minute. So this gives me the mass flow rate in the lower unit, because that's where the heat in occurs. So now I can find the mass flow rate in the upper unit by doing a first law analysis on the Cascade condenser. So if I do the first law on the Cascade condenser, it's m dot 1 times H6 minus H5 is equal to m dot 2 times H3 minus H4. So I have all these values. So I have 103.6 times 81.2 minus 36 divided by 83.8 minus 17.2. And it'll give me the mass flow rate of 70.3 pounds mass per minute. So I have the total refrigerant mass flow rate that I need with two compressors and all that stuff is the sum of the two mass flow rates. So I need both of them. And now, so the total mass flow rate would be 173, 174. And now what I did is I did the same analysis for if we just had one stage of compression, so we could compare and see the two. The COP is dramatically less, and So I'll show you what that result is very quickly. So for one stage, I'll have our normal ideal vapor compression system. And I did it as ABCD, so we wouldn't be dealing with ones and twos. So this would be 120 degrees Fahrenheit, minus 20 degrees Fahrenheit. So that establishes the temperature limits on this. And if I go through this, HD is equal to 36, is equal to HA, HB is equal to 75.1, SB is equal to 0.171, HC is equal to 93.8, QN is equal to HB minus HA is equal to 75.1 minus 36 is equal to 39.1 BTUs per pound mass. The work is HC minus HB is 93.8 minus 75.1. So that's equal to 18.7. In the COP is equal to 39.1 divided by 18.7 is equal to 2.1. So there's a significant drop in the coefficient of performance because of the increased compressor work, the lack of efficiency, the reduced QN per unit mass. And if I look at the mass flow rate, at 30 times 200 BTUs per minute per ton is equal to m dot times QN, now it's 31.1. The mass flow rate is equal to 153.4 pounds mass per minute. So the total refrigerant I need in the system circulating is 153 versus I think about 174 for the two-stage, but refrigerant is cheap. Your operating costs are going to be much higher with a single stage than a multiple stage. One other thing, and this showed a direct contact cascade system. So one of the things that happens, so if I just look at this that we had, it went down through here, our cascade condenser. So what happens is I don't need to do this with the same fluid. And so what happens, I can have different substances. So if I want to go down, I did an example where we were using R12, ammonia, whatever the table values we have. But I could let this be R12 and I could let this be a hydrocarbon, and I can get down to minus 100 degrees Fahrenheit or something like that. So I can get down to very low temperatures, but I have to use a different refrigerant. And so if I had the cascade condenser be a shell and tube type heat exchanger, then I can have different fluids in it. And so it can be a shell and tube heat exchanger. I can move down to lower and lower temperatures with that way. And so for homework for you, 16, 11 star, 16, 15 star. And now, so this talks about these Cascade systems and how they're used and efficiencies, people are curious about their home refrigerator, the refrigerator that's in a cooler. How does that work? Does it work differently? And the big difference is in how there's no throttling valve, and we use a capillary tube. So they're called capillary tube systems. And so let's look at those. And they work well, but they're not as efficient, and we'll see why.